Ladies and gentlemen, Dr. Elder Tavares, Câmara.
Well, first of all, thank you so much for having me here. It's always a pleasure to be able to come back and in some way trying to contribute and give back what this university gave me, which basically gave and sort of made what I am and gave me the ground to go further and build my career basically and choose what I would like to do, whatever and when I want to do. So that was really powerful. So, I mean, whenever I would come as best as I can to come back and or other ways to contribute, always is my pleasure. So I'm the one thanking you. So, and thanks for the whole structure that you guys made. Was oh, okay, thank you. Thank you, really kind. And, but first of most, me and Rodrigo, when we were talking about how could I present here, you know, this introduction didn't sell and give the whole picture. Basically, in my career, I started basically as a control engineer, so building blocks or building functions or managed to, you know, made FC drives to, you know, control in such a way, IPM, PM motor, some motors, but that was my world. Till the responsibilities that was imposed on me forces me to have more connection and understanding of the customer, but not only the customer, but the whole framework around me in order to put my small contribution on the whole system. So, in some point was, I must say, really challenged to be limited by the reality of the world that I needed to interact with. So basically what I'm bringing here is what I faced many, many times, which we're going to the fairs or we're going to conferences or some fairs that comes with new motor types, new drivers, and they come, oh, amazing efficiency here, and then the sales guys, investors comes, oh, that guy promised 97%, so it means that you can put this and save 97. And the reality, again, how they took that efficiency. How can we extract that higher efficiency? Can we extract this higher efficiency in all torque profiles, in all applications, and which temperature we're talking about? They never go to these details. And my point is, some of you guys, I'm talking about with the young guys, the old guys like me probably has already a career, tired, but many of you might be engineers, might be, you know, developers, but many of you gonna be the sales guys, gonna be a consultant, gonna be doing something else, but gonna be the guys that go in there and gonna sign these contracts, and gonna be my boss saying, man, I sold this 97%. Why are you not taking this? What's happening here? You're not that good, looks like, you know? And it usually is the blame of the engineer, us, or the supplier of the FC, whatever. So I'm gonna bring some examples here of some applications that I had and some learnings on this journey and the mistakes that I believe I committed as part of this framework and what I got from there and how I'm trying to, in some way, in the new projects, not commit the same mistakes or trying to have the proper arguments when I go to this type of meetings. So, if you expect some deep technical presentation, really sorry about it. Really sorry I'm gonna disappoint you a lot. But, I mean, People still call me professor, but I'm not. I'm a lazy person. Any professor here, I mean, ask how was their weekends? How was the night? These guys are working. No, I did that, and no, I'm not a professor. These guys are they're really real hard workers. I'm like my weekends, I like my vacations, so they're the professors. You know, they solve the problems. I just read, understand the problems, learn with them, and then try to apply. That's it. That's simple. So let's be clear. My name is Helder. Professor, no. I'm not. Humbly say, please don't do that. Anyway, but we already talked a little bit about myself, but my career was basically changed a lot along my period at Danfoss, where as a control engineer, I spent a lot of time frustrated as, for example, my task was to build a function to protect the DC link, to catch up the shaft while spinning, you know, without any power, called fly start, whatever, specific functions. But then we go to the customer. They didn't have actually that problem. It was something else. Or to get worse, they come with, I'd like really to use this PM motor in my application. Oh, yes, but why? No, because it's more efficient and so on. Yes, great, but why? How much would you like to save? This. What's your load profile? No, I operate full speed all the time. No, I don't actually. I operate partial load. Oh, okay. Well, when you go through, actually, in reality, you should just use induction motor here because, I mean, your savings is going to be minimal. And then the sales guys, what are you doing? But that's a reality. You know, sometimes you needed to understand the application and the profile of the customer and basically realizing that, hey, what you actually need is this, it's not that. So in the meetings, spending a lot of time convincing them, which forces me to spend most of my time in meetings than in algorithms and in papers, which frustrated a bit, but that was my career. That's why I sort of became a system engineer, may call it this way, application engineer, because that was, and that's going to be what you're going to face later in the future. That's going to be your job. That's what you needed to do in some way. But yeah, and after that I spent most of the time retrofitting, improve the efficiency of some systems in different applications, and some of them I'm going to bring it up here. And since this year, actually, I'm more focused on refrigeration applications for MCI, so containers, Maersk containers. Well, but let's establish a baseline. First of all, I don't see if most of you are electrical engineers or not, but basically, it's a little bit of my timeline of life. I started actually working with electrical motors, and really early in my career, I was approached to optimize their energy consumption, of course, to make consume less. And most of this was basically focused on replacing the motors or improving the motors, but why? Why? These are some numbers. The energy consumption is 53 in the world right now is consumed by electrical motors, but this is old. This is actually growing. The applications that I see coming up right now is just coming more electrification, more motors that wasn't there, and more FCs being used in places that wasn't being used before. Go to container ships, go to cruise ships, go to trains. There is coming more and more of these guys being placed in places that they didn't have before. And so that I can talk about fans, compressors for buildings, name it. And if you do that properly, you can easily reduce the consumption 20, 30%. So this is really attractive. And that actually make especially the sales, oh, let's go for it. The investor, let's go for it. And you, the guy, hey, let's hold the horses a little bit. But yeah, but let's step by step. Why this focus on electrical motors? And basically, if you go to the industry nowadays, and please gonna be boring a little bit for some, but soon I'm gonna bring you the problems, the fun part. Well, induction motor, most of the industry still nowadays uses that one. And still, I think in 2010, 2011, 12, many of the customers was just using induction motor with nothing fancy. And for a simple reason. An induction motor is it's a pretty simple machine. It's an amazing machine, a genius machine, where you have the stator. Once you energize the stator basically generate a magnetic field, and then the variation of the magnetic field on the rotor, the difference of the speed, the relative speed between them, end up inducing currents on the shaft, which make the mechanical, the torque, which spin up the motor. So it's amazing. So it's like, by itself, by its nature, it started to move, which is really great. And simple. That's why many applications, if they have fans, simple pumps, just connecting the grid, that's it. They have some problems, yes, but that's good enough. That was good enough for a long time. But then, I started to be approached by customers that, hey, now I'd like to have FC there, or a driver, or a frequency converter. I ended up all the time calling FC, sorry about that. Why an FC? Because with FC, we can actually, first of all, reduce the high current during power up. We can reduce repair costs. We can power saving, because we can do some methods to not only impose the needed magnetic flux needed on the machine by reducing the amount of energy, especially in partial load. That is really great for that. And for a while, that was sufficient, till I started to receive a lot of these motors here. It started to come PM motors. And PM basically the principle is quite the same, but comes a big difference here, where the induction motor you have just a circuit and a shaft that allow and be induced circulate current to generate the movement. The PM, you have the magnets. And just by thinking like this, you have the magnets there. You had already spent energy building these magnets, building to impose this field, to align the monopoles to generate this magnetic field there. So while this rotor, these magnets, interact with the magnetic field of shaft, they start to spin. And by nature, we already consume less energy because the energy is already there inside. And so for a while, I started working with some of the motors, especially low power. This is an example of, oh, sorry, too close. A small one, 7.5 kilowatts. And here you can really see the big benefit of a PM compared to induction motor, and why people were so excited at that time. Let's use that one, including myself. Let's use it. Let's go for it. Here you have an example of induction motor. First of all, here torque, rated torque, and here is the speed. And actually it's the same machine power, torque capability, but just the rotor is different. Pay attention here, especially in the middle range here, when I'm talking about 60% of the rated torque. The machine is capable not only operate close between 85 to 90% of efficiency, but hold for longer, up to 50% of rated. Meanwhile, the induction motor started to really degrade at lower, and between 50 to 25, I've dropped to 70% and even below. Meanwhile, PM, hey, I'm holding up, and here I'm between 85. So just by that, you see, oh, sounds not much, but then you have a line with 100,000 fans in parallel, then you see the big benefit. Oh, just let's replace it, right? I mean, pretty simple. But, and that, in the beginning, I started to question, okay, but can we use, and now I do these questions all the time, and I can point it out right away. Choose a kind of motor you really need to understand your application. But not only application, if it's a fan, it's a compressor, but pay attention to the environment. What's the range of temperature I'm going to face it? Are going to have negative temperatures or not? Some of the applications going to face minus 30 degrees, minus 20 degrees. Others go up to 60 degrees. This is important. Lifetime of use. I'm talking about what's the torque profile? How long are going to use nominal load, partial load? This is important. This needs to be part of the equation. And often, these are not on the beginning on these discussions when we start a product design, unfortunately. Now I bring it up, but took a lot of headache. But it's just a beginning, and you're going to understand why I'm talking about that. This example was actually really fun to work with. This is a rotative centrifugal separator. I don't know if you heard about it, but the guys people, women, guys that go to the gym know what I'm talking about when whey protein come with these guys. You have the separator, basically spin up, and they do this process called clarification process. And for example, actually a fast story, really fun, interesting. The first week that I was in Denmark, in the supermarket, I went to buy milk. And then in the shelves, they had like 5 types of milk. And for no reason, and I couldn't understand why. Like they have soy milk, milk, let milk, several names that I had no idea what we were talking about. And then I approached the shelf, and then one lady approached me, "You're not from here, right?" Oh, no, not at all. Yes, this is 3.5% content fat. This is tube, and it's at the different content levels of fat, tube 0.2%. It's done by these guys also. Smaller machines, but yes. But they are using many applications and different power sizes. Some to extract bacteria, some to extract oil from water, some use, so it's really large application of this. And when I got approached by this one, I was working in a control for PM machines and was simply to work with over voltage protection for this application. That's it, for a PM. And I was sold PM. Let's keep it clear. And it was written in the documentation that I received that they were tripping due to over voltage, and because during the solid discharge, what are you talking about? And then investigating, basically, solid discharge is basically during the centrifugal process, basically whatever material, liquid, powder, go through this path. This is spinning, and then the heavier part accumulated here. Google it. There is several animations. There is actually one really cool from Hill explaining pretty well how that works. But the problem when I was approached, and the way I was describing, when this valve was opening, I have over torque, probably provoked by, and that I saw happening, a fast drop in a mechanical torque, and then suddenly the machine was generative and tripping. Nice, but then I started really working this project, which in the beginning would be a line, would be from 50 kilowatts to 250 kilowatts. Then, of course, with overvoltage protection already mentioned, and ensure energy benefits. That's it. That was really stayed clear. Yes. Then, couple of months, I received the the data of the motor, and with a comparison with induction motor, and was amazing. This machine, which later on I learned was actually a PM-assisted Sonoram, which is a big difference. I want to go to technicality, but it's not a PM, it's a different one. So if you go deeper, there is plenty of professors here can explain, but some of techniques that you apply to control a PM machine is a little bit different, especially when you're talking about initial position detection, right? We talk about, and we suffer a lot with that. Yeah, but not only that. Here are amazing measurements of the motor efficiency. I agree, great. And see why they are so excited. Especially on this application, they should be operating between 20 to 60% of the nominal power. And this machine, by the motor, let's be clear, could be able to have efficiency above 92%. Amazing, really great. Yeah, and then let's start to work with. As I had experience with a PM, and I was so naive to operate to see this PM assisted as a kind of a PM, using the wrong initial detection, that was one mistake. Then I had a startup like this. Transient's terrible, noisy, but you clearly see the ripple, especially on a dual current. Clearly could see, man, you're in the wrong position, that's for sure. Great. So yeah, again, issues on initial position, then I learned was a problem. Big fights internally because I was requested to reuse as much as I could of the functions already developed in the company, so it was a big challenge. Anyway, but at some point, and also to get worse, once I fixed the problem of some of the functionality, let's go to the lab. Let's go to measure the efficiency. And that was the efficiency I was getting. And you look at this like, but this is great. Like at 500 and 1,000, we are above 80. And 3,000, you're above close to 90. That's great, right? No. They expected at least 92. And here we're talking about when they build contracts like this to build a product. I remember the idea is have a full package, the separator, everything on that power size needs to be more than 90% efficient, the whole system. And my motor was already lower. So unless they will save more in mechanical side, which would never happen, yeah, I needed to do something about it. And especially because they came with a design, no, look, I measured, the motor is amazing. So you're doing something wrong. But then I was using the parameters they gave me, and trust me, it was a lot of months, meetings, and headaches, and yeah, frustrations. Then, finally, I managed to find a problem. Was basically, hey, the parameters you gave me are wrong. Or, I didn't say it wrong, but has a small tolerance here, but you know, I needed to sound a little bit different. Sorry, guys. I didn't say the company, at least. Anyway, and in that time, finally, we had a function that was able at least to determine a little bit these parameters. This is AMA. It's called auto motor adaptation, but this is identification of motor parameters, basically. They send a sequence of signals in the motor in order to identify rotors, the rotor resistance, all the resistance, inductances, and so on, name it. Well, once I got finally this parameter, great. Then that was the efficiency levels that I got. Even in partial load, I was above 95. That was great. So, and then I think was the big mistake ever. Because at this point, I'm a specialist, out. Give somebody else to code. I mean, rest is just implementation. Things are done, right? It's just implementation. And then you give to somebody else. And then I was already in another project. I'm a specialist, Ben. You won't be spending your time coding, right? Yeah. Then frustration, tests was terrible. They barely could ramp up when the torque was close to 75%. This was happening. Yeah. And discussions, meetings, what's happening. I'm going through the code. Saturation that shouldn't be there. Reset shouldn't be there. Order, sequence. Basically, and that was naive from my part. I had the observer because the test setup that I was using before was DSpace-based one, right? Then the implementation, C code, using a CPU is lower than my phone right now. So you have no idea how frustrated I was because, yeah, I use an observer to be dealing with the angle, position of the motor. This is really important. The professor is going to teach you about PM, the ones interested, but wasn't suitable for the CPU on the product by the end. So I made shortcuts. By the end, we managed, but after almost 1 month. And then you have a stakeholder that was waiting already 2 years for the result, right? Anyway, finally, we managed. But from there, from the line product, that would be from 50 kilowatts, 50 something to 250. So the sales team was, yes. By the end, not really, because took too long, the lower power, you know what, let's use another type of motor to get worse. Magnets that time, neodymium wasn't that expensive, so they ended up going to neodymium because it was working anyway. Yeah, basically we almost shut down the product when it was in the end of the line. And still, we were 0.2% below the efficient expectations. And that's why it was almost shut it down. And why? Yeah. I mentioned about when we open up the valve to extract the heavy content that didn't want to discharge, I have some transients, fast transients on the torque, right? And a PM assistant, and this the customer didn't have, they didn't notice because they used induction motor before. And induction motor, fast transients, they don't care. The nature of the motor, there is a big difference between the difference between the relative speed between shaft and the stator is increasing. Oh, put more current. It does by itself. You don't need to have it does by itself. Even if you have an FOC controlling, it does by itself. A PM is not like that. To get worse, twice during tests, I lost the synchronization. And once I lost the voltage as well, but that was something else. But I lost the synchronization. Then you have the nominal current through in a shaft that don't expect to flow all that current. What did happen? Demagnetize the ferrite magnets. Took 4 months so I could get a new test set up to run, basically, because I killed the motor, basically. You know, things like this are not part of the discussion in the beginning of the product. They call product ramp up, whatever they call lately, but that was in that time. And the naive person here and many of the stakeholders didn't expect this, especially how much fight and dependency we had, not only to the motor parameters, but also to understand that the methods that some of, in that time, our motor suppliers used to determine the inductances or the profile of the inductance are different the ones that we were using. That was one of the issues we had also. So things like this, plus we have one supplier in one side of the world, the driver supplier the other side, communication. We had a lot of problems with communication, which ended up in a lot of frustrations. Now, the other new project we did completely different. This learning, of course, was used, but trust me, it was a big headache in fights, completely unneeded. But that's development. That's how it is. Yeah, now I'm doing a big jump because I did a lot of things after that. But then, even the period when I was at Danfoss, I was part of the development of a motor, a drive for a compressor, a part of a unit of refrigeration, they call. And actually, EU, and if you go Google it, there is a lot of strong legislation trying to improve the energy consumption on this type of business. And why it's so challenged for motor drives. In the beginning, I thought, oh, come on, big, it's, I was at 250 kilowatts, baby. Now you give me up, what, 10 kilowatts? Come on, this is nothing. And compressor, simple, right? Actually, I sold by, no, this is a simple one, man. You did a much complex one. And I thought, oh, so easy. Yeah, and for hardware, it's really tough, actual environment, and it's really interesting. First of all, a container, when they build a container, the container basically, first of all, experience a lot of G-force because these guys are shipped in a ship, go stuck in a truck or in a train, name it, different vibration. So for the hardware, is a bit challenging, just on the vibration in the type of environment. Especially because sea, bacteria, mold, sometimes it's covered up in ice. It needs to survive. The compressor is exposed, needs to survive that. Temperature range, that's amazing. These guys need to survive. They, in the requirement, they go to Iceland. I have 2 prototypes. No, I just checked. They're in Sweden now, but they were 2 weeks ago in Iceland. And other 2, the same line production, they're in Africa, where I'm testing different. When I tested the chamber, I was forced to test between -20 up to 55 degrees, which sounds extreme, but lately, yes, we experience in Africa, 55 easy, unfortunately. That's a reality. Yeah, so, and of course, they would like to save as much energy as possible. If any of you had experience to see a container ship close of you, I'm talking about thousands of containers in parallel. So you save 100 watts in one of those, yeah, and energy is, we have a diesel generator, right? So you got the equation. It's a lot of cash saved here. Here's just a picture how it is, how it looks like. The back of unit is basically how especially the technicians interact with. Here is the compressor I'm talking about. Here's some valves and units that I won't go in details. I know nothing about it. And here, a fan for the condenser side and 2 fans up here, but it's closed. And inside, you see just the grails here. It's how the air flows, basically. And this grade is just to give an area so the air can flow on that. Great. But basically, the principle, it's quite simple, actually. You have the one of the fans sucking the hot air. This air goes through across the evaporators, which cools down and drag it back. And then you have the condenser sucking and bringing out the hot air, and the hot air are sucked out from the unit through another fan also, and the compressor dealing the process to extract the heat so it can goes out. Google, oh, sorry. There is plenty of material about that. I won't go in details, especially because I'm taking too much time talking here, sorry. I'll speed up, promise. So I'll jump here. This is just a circuit, but here's more visible the placements of the fans and the placement of the container. But that is good animation to explain, and there is good professors here to explain how, so please. But what was my job? Here is the spec of the compressor. Basically needs to start from 600 up to 3,300 RPM. And why 600? Because this guy are, if you see, basically you have here, oh, I need to go back here. Here's the compressor. Basically part of the stator is the shield of the compressor. So you have a manufacturer building the motor, this part here, and then it place it inside the cage of the compressor. And this compressor, and this is important, has 4 pistons. It's important to that, which regulates where the hydraulic fluids and gas go to where somewhere else by these pistons here. And here also is the FC. Well, goal here is, hey, let's save 20% of energy compared to the unit that we have induction motor. Yeah, great, easy. I mean, it's a compressor, right? Yeah. That was the hard reality. This is, and by the way, this simulation, this can be worse actually, because, yeah. Mechanical systems. This is a pressure bar on the pistons. And I think the most important is this black curve here. This is first where I'm starting. The motor is facing already 5 Newton meter on the start. And as soon as I'm spinning, I'm starting to have a ripple of 80% of torque, of the nominal torque. That's the torque profile of this compressor, the piston compressor. And can get worse. May I ask you, what should I do if one of these valves break and I'm mid of the sea? Like this. Suddenly one piston breaks and then the torque becomes like this. What should I do? Should we set an alarm and stop the compressor? And stop the reefer? With, you know, full of tuna, which is pretty cheap, right? Or the last cargo that I heard about it was 600 millions and it was just a container. Should we stop, right? No. Keep going. Needs to run. Gonna consume more energy? Yes, but needs to run with this torque. And then I'm asked to put a PM. Yes. But why all excitement? That was the numbers gave me by the motor manufacturer, where you have clearly the difference between a synchronous motor and a PM motor. Again, as we talk about it, how good these guys are, especially in partial load. So this brings a lot of benefits for the customer. And it's important to point it out that I have many, many cases where their operation were close to nominal, and the power size, and considering that was just, you know, 2-3% or saving for the power, I basically recommend, man, don't put even FC, put just a contactor, that's it. You know, why? You know, there is high efficiency motor nowadays. Why? But in this case was clear. Yeah, clear benefit. But, yeah. Then we started to run. Oh my God, yeah. The challenge for our supplier now, because in that time I'd solved part of the problems, was still induction motor, was a type of PM, then they replaced for a PM assisted, then they started to have several challenges, and one of the big challenges, I must say, is basically they ended up needing to make a new software, so a new baseline for their maintenance. Their problems, not mine, but anyway. But what I would like to bring it up here was the shocking part. They spent a lot of time to make it work. Different initial position detections, tests to optimize to really get the proper parameters of the motor, because again, as we saw, it's really dependent. Then Danfoss came with another team came with a software that actually in partial load could minimize the flux of the induction motor. It's actually not so, it's quite common actually function, but then they managed to make that work because it's a bit dangerous, especially on this torque. If you minimize the flux, you ended up losing a little bit of the torque, so you have a risk to, you guys know better than me, and you lose the synchronization. Bye-bye. Yes, but we manage. In that time, I was even part of that project, but at some point they managed to suit on this frequency converter, right? Look the efficiency, or look the power measurement that we got. This is a unit without NFCs, contactors, things like that. Then you have with the IM, induction motor, with the flux optimization, 1.58. With the PM, 1.5. Imagine the frustration when you spend like 2 years, where is my savings? Right? Yeah, was a big bombshell. But that, again, as I was talking before, a PM is a great machine, is an excellent machine, but some torque profile like this, when you do this efficiency measurement, the power consumption measurements on the motors, yeah, they are quite efficient, but their nature, they have some limitations compared to induction motor. Induction motor, something like this, if you don't control properly, they keep it running. The only thing during the transient, they consume more, but then they settle down. These PMs, no, basically they lose and bye-bye, and you lost the machine. That's it, you know. So at this case, basically what was done, and I know because later I left the team and did something else in my life, then these guys said, man, I need to over-magnetize the machine. I needed to hold it, otherwise I would lose the sync. But over-magnetizing, I'm consuming more. That's a challenge. So the conclusion was, use induction motor, man. It was more efficient. You just needed to tune a little bit more. That's it, you know? Didn't we know that in the beginning? Actually, I had a feeling when I saw that torque. But, you know, again, excitement that, ooh, take it easy, guys, you know? Sometimes, that's why it's so important for me to you guys to listen, because you guys, most of you would be my boss. So please listen. When I say, man, please, what is the torque profile? Where is the temperature range? Which CPU are you going to be using? This is important. What is not trivial. Unfortunately, my lost hair, my experience shows that. I face it on pain. Okay, and then during that time, I joined the group, and then would be easy sailing in theory, because would be, oh man, I have 3 more fans there. Let's put FC there. Let's put a PM there, and it's just a fan. Oh, well, yes. And then we saw that measurements, that efficiency. That's gonna be easy, right? Easy, great. Yeah. And then, of course, uncomplicated profile, smiling. So retrofit gonna be simpler. I mean, easy sailing. That was a misconception. And then someone in the meeting came with the idea, oh, by the way, you have a DC link, right? You can actually extract the 24 volts there and supply everybody else, right? And then, yes. Well, leave the FC idle, right? And the FC supply everybody else. Yeah. And honestly, but trust me, I didn't see any problem with that. Well, why not? Great, and all excitement. Trust me, all the test was going great. No joke. Basically, the idea, and also that was the most clever part, because some of the experts, I work with a guy called Christian Koskil. He's amazing. That guy is one of the reference nowadays in refrigeration in Denmark. The guy is a genius. At work as hell, but the guy's amazing. And he realized that, my man, look, here is the energy distribution on reefer nowadays. Basically, you have most in the compressor, and then you have 20% on the motors, evaporators that was up there, and then the condenser. With FC, and if you do some tricks, you can actually extract a little bit more and save a lot of energy, because then you take all the consumption of the PM, of the induction motor, and brings a little bit to the PM for in terms of to operate the reefer and turn the whole system more efficient. Was just a theory, was just an idea. But then, you know what? Let's focus on the FNFC, and yeah, let's play with that. And we are actually upon to start this project. And the other big contribution, that's the standard unit, right? Here's the whole contactors controlling all the fans, turning on all the compressors, and that's the new one. Wow, right? Especially the technicians. Talk with the technicians, they would love this. Great. Easy sailing. Yeah. Oh, why is not working? Oh, yeah. Yeah. Then we started to have a little bit of problems here and there. By the way, this test was so amazing. Unfortunately, I couldn't bring pictures of that. But I put the container in a big container climate chamber, which basically, yeah, 1/3 of this room. You put a container inside, and then you cool down to different temperatures, like -20. You can put up to 60 degrees positive, and do a bunch of tests there to really evaluate how these guys operate in different temperatures, and also to evaluate how much energy are we spending to cool or to heat up something inside the box, also the container, right? And then one not good news was, here was amazing, like this, interpreted, sorry about that, but like this is operation mode. The box I'm talking about inside the container, and ambient temperature is outside. And then 40 degrees, 38. Of course, thank you, Excel. He made a division here. Sorry about that. But it would be minus 20 divided by 25 here, okay, or something like this, or 38, sorry. But sorry about that, anyway. And here's other similar set points. And lifetime of energy use. This is the percentage of the conditions here, the container facing along their life. 35% is at cooling something inside at -20 and ambient temperature of 25 degrees. This is rely on data that we have, how our customer used it, all general customers. Then that was not so good news. We saw, we are just saving 6%, and we expected here -14. Even though what we measured at this condition, this was much better. The investors especially, hey, this is not good. This is not good enough to be a product. Anyway, and then we found some problems on the software implementation anyway, and then came the big bombshell. Was a bomb in that time. Again, easy sailing, right? They promised me that. Well, during some tests in the lab, we started to see the circuit breaks was opening when we are shutting down. We are testing, running the test, and suddenly we're shutting down. 30% of the cases, I did that. Trust me, several times, because it happened once, so I needed to check. I spent like sometimes hours on, off, on, off, on, off, again, you know, really. I didn't have a robot, so that was me. 30% of the attempts, this happening. And then measuring the currents, I saw this. And why this happened? And my customer didn't see that. And then, of course, the problem was the driver that I put in the fence. Of course, is their blame. Then I went to the old unit. Let's test. Tuck, 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 tuck. Nothing, nothing, nothing. And then I kind of, I realized one thing. The old unit, we had the switch, manual switch. So the person, I don't want to anymore, turn it off. And that would open a manual solenoid, which open a contactor and shut it down the unit. Simple. You know, new product, new interface. Let's remove the manual. Now it's a digital button. So the guy on the field, what they do, they go to these guys here and then switch it off. I don't know if you know which type of switch, but I know, I saw you have that in the lab, is a three-phase circuit break, which basically are 3 metal plates. And then when you're switching, they open at the same time, right? No. You have this behavior. These are the 3 phases, and then you have the ground current. When they go through, and then the engineer, which didn't design anything there, electronic-wise, go to the EMC filter, the conductivity one, and then measuring the current there. No joke, I put apart the FC. Did all the tricks, damaged some, but that's my life. People know me, I damage a lot of things here. There I do the same. Then the current was there. Nice. Let's have a talk to the team. Danfoss, look what I discovered. And then we talk, but we never saw that in the field. What's happening? Called another company. All these discussions. Let's redesign the AMC. Great. We attended the requirements. Yes, maybe. Because that was a challenge. We started to fight. Okay. Basically, what happened, what discovered is, what I found out by the end was, to save money, they had a chokes, induction chokes, right here. And there's professors here, I don't want to go to details, but EMC conductivity, you have 2 ways, induction-wise and capacitive-wise to filter. Please, Paulo, you know that much better than me, right? You can do in both ways. But who is cheaper, inductance or capacitance? Capacitance is much cheaper. So basically, in the second update they did, is attending the requirements, they reduce here and increase here. I had more capacitance there. To get worse, I put an extra FC in parallel with that one. What did happen? I just had more capacitance. Well, I was having tripping all the time when I put it FC. So we joined the teams. I had a meeting with 3 companies. We spent like 6 months to arrange everybody, please, let's sit together. We need to sort that out. Because I know you design your MC to attend some requirements, you as well, but we're having this problem. Great. And also attending the MCs because I needed to actually, here was actually at Danfoss. This is one of chambers they have to measure radiator emissions. It's an amazing place. And I needed to prove, guys, yes, but let's minimize the capacitance, and wasn't sufficient. So was a team, 2 companies talking together in order to find an agreement. Or how much less capacitance I can have, not having thrift, but still fulfill the requirements. That was the level with both products. And that is still, I must say, is still a challenge today. How much should I ask from one from another? But we're happy right now. At least we were. Because this happened. Easy sailing, right? Some of the prototypes, now we are a different phase, prototype fine, but let's go to the container ship. Put in a container ship. Suddenly we started to see FCs blowing up. Was blowing up, the DC-link was just exploding. And okay, what's the condition? Let's see the data log. Well, the FC was standstill. Nothing was happening. And then you blame quality, you blame the suppliers, you know, meetings. But you know, that's what I like. Never forget theory. Never. Tools change time to time, coding language changed, but the theory, the principle, the physics never changed. I remember long time ago when I was studying, they were talking about residual currents, and especially the big motors. And then I was looking in the schematic of one of the container ships. Then, and actually it wasn't me, it was amazing guy, Kim. It's one of this engineer, it's amazing. He pointed out, Helder, I think it's this big baby here. And then we were talking about, and oh, what the size of this one? No, not this one. This is a 300 kilowatts motor drive, but there is no connection to the ground. There is no, because this is a container ship. They don't need to, there is no ground. I mean, where's the ground? There's no ground. But it's a big motor. But you don't have just this one. You have this one, you have the two for the water, and in one section, you have several sections with these big babies there. And these guys there, they have parasitic capacitance. Parasitic capacitance, so basically is a connection, even though virtual, but they have a connection to ground, but you don't see it because it's a capacitance that is there just due to the amount of current they have. And then come us with the new MC, everything was fine. This connection here. Closing the circuit, basically they measure there. They had 150 watts. And the drive is standstill. Remember, standstill to supply 24 volts to everybody else? Yes. They have just 7 volts consuming, and I have 150 watts flowing around. And then this thing, whoop, 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 whoop. That's it. Yes. Imagine, of course, it was a relief when I found out, because basically put a relay, put a measurement, or keep monitoring the dislink, and then, you know, inject the C on the motor to consume. There is a way to do, but took like forever. But not only that, was a surprise of us. Now I'm talking about MCI, writing the requirements, but also the suppliers. Whoa, I did that for many, many years. What phenomenon is this? The other one, same story. They didn't expect that. Of course, some specialists on marine, they would see that. But how many are those? How many do we have access? We have this big organization, we have so many problems on communication. And that was one just example. I know somebody faced this problem. Danfoss, for example, sell things for the marine. They know this problem, but we didn't. And even the division that I was working didn't know that also. But was a relief. But anyway, soon everything sorted out. At least we started to also play, we got a chance to play a little bit with the system, trying to understand the system, because for some was a big difference, because the plan was, let's use the same software, don't change much. Let's use the same software, put FC to control the fans, use the same reef, a control unit. I'm talking about, you know, set the temperature of you wish to be inside the container, and then the controller deal how much the compressor is going to be running, the speed, how much pressure. They deal with that. That's the controller I'm talking about. But they have a software, they have a sort of algorithm and sort of procedures that the algorithm follows. We might be changing that also, because we already could see that, which makes sense actually a little bit. As we have PMs here, and here's induction motor based, now we would like to increase a little bit the consumption on this guy here in order to reduce the consumption of the operational time of this one here. If this operate more, this operate less, and the whole unit gonna save more energy. And actually, we could actually prove a little bit on those. Basically, by manipulating part of the speed, this is the operational cycle of the compressor, for example, and when the max speed, by just changing the speed, increasing the speed for specific levels, set points, the operational time from 3.5 minutes was reduced to 3 minutes, reducing just and the compressor around 100 watts. And 100 watts, this is nothing. 10,000, 20,000 containers, 100 watts. This is a big, big deal. But yeah, at least that was something, was a relief. But from here, honestly, I still don't know. It's clear, EMC conductivity, it counterattacks with RCDs, with the design of to protect RCDs. It's one each other against each other. So there is a trademark there you need to play with. And I'm not expert. This is not my, but unfortunately I was forced to influence on be part of the discussion. Remember, get out of, even though your task is this, but once you engineer, once you represent a company, you needed to, different hats. If it's necessary, you need to go through. I know nothing about power electronics, but I needed to. This, I needed to. I need to study, I need to understand in order to, hey guys, what I see there, it's something maybe related to that, and you know, that happens. And that's your, which in some ways is fun because you ended up learning a lot as well, but can be a challenge, trust me. And, but also for me, it's really clear talking with some of the guys, especially the real customer, in my opinion, which the technicians. They are the ones on the container ships dealing with these guys daily. And they already told me, man, we see phenomena. We see more and more of these FCs, frequency converter drive systems, on the containers, and bringing phenomena that we don't understand, are new things for us. And us as a suppliers would, okay, how can we make the requirements? And that just going to be more and more complex. I already feel that. But that's good and bad news, you know. Reality is there is no easy sale that I thought about, you know. But that's how it is. That's being engineer is our life. It's there, solving problems, right? It's clear that the FC brought some benefits, but it's quite visible. Again, don't change the reefer control. Oh, actually, the system is different. The optimal point of this unit is something else. We actually need to find where it is. And we're going to actually, we might be starting in a few months, actually, this study. Where is the optimal point? Which is quite crazy. We're going to be consuming more energy in one end to reduce the consumption of the whole unit, which some way makes sense for some, didn't, but it's proof. Yeah, but yeah, new phenomena, yeah. But in general, what sounds almost therapy, right? Just frustration, nothing worked. It looks like everything I did. Look, I didn't want to bring here new theories, new techniques, new things that are implemented. What I'd like to bring it here, it was
Thank you very much for your presentation, Dr. Elder. So now, somebody have some questions? Any question?
Okay, thank you. My name is Paulo. And have you some methodology to obtain the iron loss in this project?
Excellent question, because that came up, but no, unfortunately, we didn't have time to go deeper on that, especially because just recently we spent time really focused on. I think we are focused. Looking somewhere else when we're talking about energy efficiency, right? And then suddenly, and again, we were so naive to just, we just take the motor from the supplier and that's it. but we didn't, and there's many papers showing, and literature showing, hey, how we interact with the motor also impact the iron loss. But yeah, unfortunately, probably Paulo had the same experience as myself, but yeah, it's unfortunately no, even though I tried, but no.
Okay. Another question: how to overcome the magnetic saturation and cross magnetic saturation effects in this motor to obtain high efficiency?
Yes, especially yes, it is, but there is some, and now I'm a bit out of my comfortable zone, because there is also ways to optimize because one of the issues that basically, again, my humble opinion, happened is the way we control the motor, we use a sinusoidal way to control motor that clearly has a back EMF that is far away from sinusoidal way. And we ended up imposing ripples that wasn't there. It's not even due to the application. Just the shaft by standstill, there is a ripple there that we impose there. You know, there are some ways to reshape the magnets in order actually to optimize and give a better back EMF. But, you know, would be really nice that we could sit together, you know, driver, developers, and the motor designers in order, hey, that's fine in between, or help me out to control you better, you know, that, yeah. But
Okay, my last question is about the cooling systems. And have you using the liquid cooling system in these motors to obtain high efficiency?
The compressor motor actually has a cooling system, and is hydraulic one. That's why he's inserting inside a compressor that is a whole fluid going around the motor. So that is already does an induction motor. The challenge what we have is, again, in the fans, there might be beneficial, but you needed to hold the horses a little bit here, as you saw the environment. It's not only about, again, it's not only about looking the motor. We need to look at the system, the whole system. There is vibration, there is this, you see sometimes the drop in the containers is not, so mechanical wise, environmental wise, is really harsh. So whatever solution you come up with, you needed to remember, and by the way, warranty of 10 years. So you need to replace the part for free. So you got it, right? I won't be adding something, yeah, to save few watts, but then keep breaking all the time. Bad experience and costly. So yeah, the fan maybe no, but in compressors already like that. And that is also in the, and that I couldn't show in the picture there, but there is in the part of the unit. In order to use the C, you actually extract, there is a pump sucking water from the sea to cooling the system also. That is, yeah, but not direct the motors, but the part of the refrigeration system. Basically, it's just a shower. You know, the evapes that I was showing there is a shower going through there, basically. Yeah.
Thank you, Elder, for sharing your experience on that. I appreciate that. This problems really shows that you need to go up to the end to get a satisfied customer. And I don't think that artificial intelligence or fuzzy logic or digital twins will solve the problems as you solve it. So you need hard work to reach that point. I just would like to add one more layer of complexity. It's not related to refrigerated container, but refrigerated trailers that are driven by the truck up to the port, And some port authorities are limiting the use of diesel for cooling that trailers. So how about adding battery on that to run this during this time? And I have seen some challenge on that, and especially at 48 volts. That's a nice
Yeah.
challenge. What do you think?
Man, the mind can go wild. Yes, we actually had some ideas to spend time building these prototypes. Yeah, because we were already requested. Because you brought, I couldn't bring everything. Like, you brought 2 points here that I forgot to mention. You had, and many of you guys had the same experience as myself. You spend a lot of time tuning, adjusting, feeling the application, the motor, and then, hey, technology level done, where you documented everything, somebody else gonna code that. That's why actually, I mean, got some problems, but Typhoon Hill combined with model-based design was so good, because then finally I got a chance to, whatever I was testing, the code was quite similar the one I was running to the application, which was good. But for many, many years, somebody else was doing that for me. And as I mentioned to you, and again, it's due to the framework. So that you brought a really good point. You mastering the skill to understanding, and you put it out. And some specifics, it's not only about which observer, which gains, which design, but minor details in the implementation, where the reset on the saturation can happen, and which time instance, what to do if the resolution is not that big, or if the noise is, you know that because you implemented the code and you saw these phenomena, and you needed to write 2 theses to document everything, the final adjustments, and you can't. And then suddenly you gave somebody else. That's one point. But yeah, the battery, I couldn't bring about the nice waveforms that we have from generators, especially from, imagine you have a container in Africa, they took it out from, they had no power, put a generator from an old engine from a truck. The waveform is far, far away from balance and sinusoidal, and it's the same container with that torque ripple. So imagine how beautiful it is. And so yes, we would like to have time to spend with a battery and see the other phenomena, because we clearly going to have some benefits, but we see we might have some issues as well. As I mentioned somebody today, one concern that we really have right now is, again, this industry in particular, they didn't have much experience to have so many FCs in parallel, and now we put a lot of parallel. And any experts on microgrid, you have really grades here, man, they're gonna say, that's gonna be beautiful, you're gonna have some problems, you needed to do something about it. And we don't know. We actually spending time. I'm actually gonna later, someday next year, started to work with that also. So, but Paulo, there is too many things to do, too many corners to explore, and again, I'm the guy that, needed to firefight, and I know this is not done. I know something else will pop up, I know, so that's our daily life, right? So, yeah, but good point, thanks.
Any question? Igor.
Yes. First, thank you very much. Thank you very much, Elder. I'm Igor from UFSM, and first I'd like to thank you for not giving up of arriving here, because it was hard, For who doesn't know, Elder arrived this morning in Santa Maria after some flight canceling and a lot of delays, which were not your fault, but from the destiny. And my question is very general and it's not technical. So thank you for the colleagues, the professionals who did the technical questions. But you are a former student, okay? You got your PhD from UFSM, and in this auditorium, I believe there are many students like me who are in the beginning of the career, and do you have some tips, some suggestions, some advices for us, and mainly to the ones who want to have an international career? Because I know that you mentioned to Rodrigo, and he shared with me that you have a debt of gratitude with FSM. So I believe that if you want to share this experience of yours, this is the moment. Thank you very much for being here again.
Oh, again, it's quite the opposite. I'm really glad that I could meet these guys, Hennis, Humberto, Hilton. I mean, yeah, they shaped my life. They really shaped my life. I mean, so, and they gave me the ground. Again, focus on principles. Test to break. You know, that was the guy that came and set up in short circuit. Whoa, this is not the. No, but wasn't ready. No, so he's not ready. Blow up, he's not ready. Breaks, till made it work. I mean, they really shaped me, and whatever is just gratitude, and so whatever I can contribute is, I always will try my best, even though 24 hours in London airport wasn't that great. Anyway, but here I am, and I'll keep going. Paulo, or somebody else needs to help me out here. I don't. The only thing I can say that might contribute for all of you, it's never forget about the principles. You know, I'm saying that because I did completely the opposite. Some of you might remember, the old guys, that I was really fond of putting my mouse upside down because I knew all the shortcuts, for example, on the Windows. I knew all the shortcuts on MathWorks, MATLAB, things like that. So I spent a lot of energy memorizing that one. What's the point? I spent a lot of time on C, building libraries on C and mastering C, and then come Python. All the libraries ready. You know, but just later in life, for example, I work as a control engineer. Instead to master, you know, drag this mind, Hennis was my professor in Control 2, and I was memorizing shortcuts instead to drag this brain and feel, understand. It was a life. Later on, I needed to revisit the theory. I'm not talking about reaching the values, calculate the bandwidth. No. I'm talking about feeling. You see the signal, and the phase shift is coming due to that. Because you feel, you see and you understand. You know, I know it sounds philosophical, but honestly, for me, it doesn't sound like. I really feel motor, really feel some elements that just later in life, you know. So, guys, the only thing I can say, take as much as you can right now as an opportunity to focus on the basics. The rest is tools. Even PM Motors, I was talking too much about PM Motors. PM Motors is a tool. It's the how to solve a problem. Understand the problem. And what's the goal here? Save energy, minimize torque, minimize harmonics, understand the principles. The rest is, I just mentioned an example. They was filtering using inductance. No, let's use capacitance. You can use something else, active filter. No, but focus on the principle. And that's it. And don't be afraid. I mean, I know you in a different time of your period. I was there, where you finish your studies and you don't know what you're gonna do, and sometimes you'd like to go a safe place, or you know what's the easiest path to just get a job. But trust me, man. I mean, I'm not that clever. Many of my professors know that. I'm not that clever. But at least I was shaped well by them, and I had a theory, but I never was afraid to work. That's it. And all the successful guys that I know, they simply, they don't give up. They keep going. They keep working. They if they have doubt, they reach out. Don't be afraid to ask. Ask. You don't know everything. I mean, the world is too complex now, man. Look how many, if you actually pay attention, how many different theories I went through during this presentation. I started with a PM, but I was talking about completely bananas, something else. You know, and I didn't know that thing. I needed to spend time studying. Usually, some professionals say, that's not my field. But I was mentored by these guys. And these guys, I cannot forget Torri, that worked with me when I was in Veggie. Perfectionist and goal theory, goal to understand. I mean, use these guys. Try to find the experience one, and not only talking about the educated one, I'm talking the experience that, you know, the guys who has experience, learn with them. Take the opportunity. You have an amazing brain now. Your brain is still young. Learn as much as you can. Commit many mistakes as possible. Break things, but use this time to learn. Because later on, you're going to have fun stories, at least, yeah, and survive probably, but yeah. But honestly, that's all I can say. I don't feel like I can, you know, give more than that, yeah, honestly.
Thank you very much, Elder.
No,
Thank you very much for sharing this and for your presentation. It was excellent.
Douglas from UFSM, thank you for your excellent, energetic presentation. I liked so much, and I would like to focus on something that you told about the principles. Once upon a time, a professor told me that you have to learn. Well, I asked him what I have to learn, and he told me you have to learn mathematics. You have to learn the basics so well, because switches, thyristors, transistors, MOSFETs, IGBT, they will change over time, but the mathematics, no, it will stay. The basic stays. My question is not so technical like the colleagues, but it's more like for a curiosity that I was talking with Igor. How this container ship keeps the compressor and all the system running along the way that it must travel, where it comes the electricity, the source of energy.
We just heard today, one of the examples comes with a digital generator. Sometimes a brand new, sometimes an old crap. But yeah, or comes from solar panels, comes from wind. These guys, they need to survive an ice grid in the harbor in Europe, really high regulated. Sometimes needs to go to my prototypes in the middle of Africa, and I think it's in Congo right now. I don't know it's the quality of energy, but needs to survive. Sometimes it goes to India. This go all over the world. That's their reality, and that's the business. Many of you has Apple Watch here. How do you know they come? Containers, man. They need, and where they are produced? Over there. Do I really believe they fly up to here? No. You know, they need to survive. And no joke, and some of these loads, they are really expensive. It's crazy. It needs to survive. And that's it. And again, this business is, hey, I buy something, how long does it take to pay me back? Also, this is an account. And it's not only containers. I already gave 2 examples, but I had much more, which the principle is the same. I'm investing something, you promise some savings, some optimization, which results also in savings in cash. How long does it take to pay back? That's the business. So that sounds too crazy. A container, it's so harsh environment, surviving 10 years. But yeah, it needs to be cheap. That's the joke. It needs to be cheap also. Yeah.
Thank you.
More questions? That's okay. When I met Elder, I was a young man. When I started at Sepoc, I was 70 years old, and Elder was a student of Elder worked with Professor Willson in a doctorated course, and Elder Elder in this helped me. I did my technical course in Cechisme, and Elder, I learned a lot of math, simulation, MATLAB simulation, electronic simulation. So I glad Elder. So Sepoc 2024 would like to give a gift. Douglas. A simple gift, but is a symbol of Rio Grande do Sul. Thank you very much.
Thank you.
Terminou? Pessoal, antes da gente terminar, eu só gostaria de passar um aviso para vocês. The English está sorteando algumas bolsas de